Good morning, ladies and gentlemen. I hope you all had a good evening yesterday, slept well, and you are fresh to start a new day with, again, a hopeful lot of information for you. A couple of announcements. Like yesterday, the hotel asked again to fill in the list for the lunch this lunchtime. So please fill it in, then you can have your lunch then. I passed it around, and please return it to me. It should be handed over to the hotel before 10 o'clock. So can I give it to you, and can you pass it around? Thank you. Then again, I believe we have a couple of new delegates. I already met one of you. Maybe there are more delegates now, which were not yet here yesterday. Okay, thank you. Welcome also to this tutorial. On the memory stick, I have to yesterday. It gives the evolution of the different ITOT fiber recommendations over time, and we see also the input, the influence of the developing technology behind it. I do it quickly. We have seen it already yesterday, but as a start for the rest of the presentation. We have seen that in the first phase, we can recognize around the late 70s, early 80s, we had only multimode fiber as a tool to build the first systems. And that was the reason why G651 was created. But already soon after that, the second phase was starting up in the mid-80s with the called the dispersion unshifted single mode fiber, and in this case the G652 was created. And over time this recommendation developed via B, C to the last one we have at this moment, G652D. Also in the same time frame, we could say, another fiber was created, G654. It's called now Cutoff Shifted Fiber, and the original time it was also mentioned a loss optimized fiber, especially optimized for 1550 nanometer. So it has a higher cutoff, and it is not used at 1310 nanometer. Then the new group of single mode fibers was created, dispersion managed fiber we call them, and the first version of that is the dispersion shifted fiber G653, which was created so in the 86, 87 time frame. However, it was optimized only for one channel application, and it was very quickly after that new developments made this recommendation less interesting, so to say, because new developments came up. One of them is the advent of optical fiber amplifiers, so you could make much more cheaper amplification of optical signals, and also the introduction of multiple channels in the same transmitted over the same fiber was created. Wavelength division multiplexing, which can be dense WDM, where the channels are very narrow spaced to each other, or coarse WDM, where the channels are more far away from each other. These new techniques asked for a new fiber called G655, and that is the one which was created so in around 1996. I will come back on that later, why this fiber was needed and why it is different from G653 and more or less taking over the need of 653. Then in the last phase we are still in, I would say, another NZDSF fiber was created, G656 on one hand, but we also see that the market more moved to fiber to the home applications, and there the need for band insensitive single mode fibers came up, and that was created in this recommendation G657. At the same time also a new multimode recommendation was created, more or less overtaking the older G651. So this one is G651.1, and this is now in force since 2006. Over this time frame you have seen the development, first in time division multiplexing, so increasing speeds of transmission systems, up to 10 gig, so around 1995. And then the new techniques are created, also indicated already over here, wavelength division multiplexing, where you have multiple channels on the same fiber, increasing the capacity you can reach over one fiber. Okay, this is the overview I came up to yesterday. Let's now have a look on the different fibers a little bit more in detail. As said before, you can find it back again in section 9.1 of chapter 1. The first fiber is this multimode fiber. Nowadays it is G651.1. It is a 50 micron fiber, graded index. It replaced the older one, G651, which was the first recommendation in ITU on fibers, created in 1984. G651 multimode fiber is the old one, started the first in fancy optical fiber communications. The new one, the dot one, is more created, more developed for use of internal networks, like in multi-tenant buildings, so really a fiber to the home application. It's supporting, for instance, 1 gigabit Ethernet systems over a distance up to 550 meters, which is enough for this multi-tenant buildings. And it is used for 850 nanometer. Okay, then I think the most important recommendation we have in our collection, that is the recommendation G652, which is a standard single mode fiber, and it was created in 1984, and up to now it is, I will show that also later, it's the most widely installed single mode fiber, so it is one of the most important fibers we have in our collection. It's characterized by a zero dispersion around 1310 nanometers, so in history, the fiber started indeed to be used first at 1310 nanometer. Only later, around 1988, also the third window, the 1550 nanometer application was also mentioned in the recommendation. Later, around 2003, new versions came to the market in which the water peak was reduced to a low level, so we call that low water peak fibers, and it was also ensured that these fibers didn't have any hydrogen sensitivity anymore. That was incorporated in the specification. So in this case, this fiber, this new version, that is the 652C and D versions, can also be used around the water peak, and that is important if you go to coarse WDM systems where you have wavelength channels over a wide range of the wavelengths band. Also, PMD specification was added at a certain time, and at the moment we have 4 categories, and they are indicated over here. We have 2 older versions. The A version and B version are not specified in the water peak, so they don't have any water peak specification. It started with a rather large PMD value of 0.5 picoseconds per square root kilometer. Later, a tighter version was added to that, the B version, with 0.2 picoseconds per square root kilometer. Then in 2003, the C version was added, the low water peak fiber, as indicated over here. It started with still a rather high PMD value, and later on it was taken over more or less by the latest version we have now in the book, and that's the D652D version. Again, it is a low water peak fiber, and it has a PMDQ value of 0.2 picoseconds per square root kilometer. Incorporating in this low water peak specification is the fact that these fibers are being tested for hydrogen sensitivity. We call that an hydrogen-induced loss. Fiber makers are checking their fibers at a regular interval, and that should be incorporated in the total attenuation at 1383 nanometer. So what we see here, a typical attenuation curve of a G652 fiber. The D version has a specification that over the whole range, the cabled attenuation should be smaller than 0.4 dB per kilometer. ranging from 1310 up to 1625 nanometer. And at 5050, an additional specification is set of a level of 0.3 dB per kilometer. You also see here that this fiber is a non-shifted dispersion fiber. It has its zero dispersion around 1310 nanometer and has a dispersion around 5050 of less than typically 17 picosecond per nanometer kilometer. So this fiber can be used in the different bands indicated over here. Maybe you have seen that somewhere else, but I repeat it again. We have an O band normally, which is characterized in ITU from 1260 to 1360 nanometer. That is the first band where optical transmission started. We have the E band, which was now becoming available with the lowering of the water peak. So with these fibers, the C and D fibers, we have this band now also available, which is running from 1360 to 1460 nanometer. We have also an S band, short wavelength band, it's called, and this is running from 1460 to 1530 nanometer. The most widely used band in the higher wavelength range is the C band. It is the band from 1530 to 1565 nanometer. Most of the systems running at the moment in the third window are using the C band. And in addition, also now increasingly the L band is being used. The L band is running from 1565 to 1625 nanometer. We have also a U band, which is used for maintenance activity. So there's no real transmission taking place in the U band. That is finishing up to the high level of the L band. So here you see that the whole spectrum from O band up to L band now can be used for these kind of fibers, the C and in particular the D fiber. Is there any question on this fiber? Yes.
Excuse me, I'm back on my question, on yesterday question about water peak. If I see the table for different categories for fiber, A, B, C, D, B and D, sometimes the attribute for them seems to be the same. And the big issue is the difference in terms of water peak, especially for B. So I want to know in details the impact of water peak for a transmission, if I'm transmitting on it, B and D, and exactly what is the meaning for the water peak.
Good question. The fact that we have a water peak in this range for the B fiber, which is not specified, that means that such a fiber can have a much higher water peak. It's an uncontrolled water peak, so to say. So it can be much higher than the 0.40, which is needed for transmission in this window. So that means if you have a B fiber, it is quite obvious that the E band cannot be used for optical transmission. So it's excluding, then you only have left over the O band and, let's say, the S, C, and L band, but the E band cannot be used. And for instance, for coarse WDM systems, if you ever want to use this network also for coarse WDM, some of the channels are also positioned in this E band. So that is then the limitation. And it's up to you whether you would like to take that risk, whether you want to use B fibers, or that you want to be more future-proofed and use D fibers, which have the whole band available from O band up to L band. So is that an answer for you?
The second question was the meaning for water peak. And now another question should be, if I'm transmitting with SDH technology, can I use B, or it's better to use D? And if I'm using DWDM, or can I use B or D? Thanks.
Okay, my recommendation would be to use D fibers, because in that case you are really future-proof, and you can use also, you can also use the E-band. If you are installing B fibers, you still can use it and many wavelengths, of course, but not anymore in the E-band. So then you are limited a little bit in your future use of this network. And it is for that reason that we have this fiber now as the most recommended fiber we have in our collection. We still have the older versions in ITU documents, also partly for historic reason, that we know what, once we have installed the older fibers, we still know what kind of specifications are related to those fibers. ITUT is not deleting older versions. They often keep the older types in the booklets. But I would say the D fiber is the more likely and the more future-proof fiber of these four subcategories we have in the 652 class. So for future-proof, I would recommend the D fiber. Yep.
Just to come back on his question, what exactly the meaning of water peak?
The water peak is created by an incorporation in the glass system of OH ions, which can happen during the manufacturing of optical fiber. In the older days, manufacturers didn't care so much because there was no demand to have this water peak to a low level. So in those days, the water peak was somewhat uncontrolled and could have large values up to maybe 1 dB per kilometer. So the reason is that you have incorporation in your glass of OH ions. Now, modern techniques of fiber making take care of that. We can reduce the incorporation of OH ions, and with that, we can lower the, in the past, high water peak to low levels. So this is the level which is in the specifications. Well, what you can see is, what you can measure is an increased attenuation expressed in dB per kilometer. So that's the result of having an OH peak there. It is a phenomena which is creating in, like I showed you yesterday, that attenuation, spectral attenuation, can be built up out of different components. We have seen that Rayleigh scattering is acting on the fiber, which is this wavelength, strongly wavelength dependence factor. We have infrared absorption that is increasing the absorption and increasing the attenuation from, let's say, 1600 nanometer and higher. And the water peak is also a local spectral phenomena, which is only acting in this wavelength area, which is adding additional loss. So it is only a partial loss over the whole spectrum of the wavelengths. And it's contributing, like the other components, to the total attenuation spectrum of the fiber. So optical signals will see attenuation, higher attenuation in this region. That is the effect of having an OH peak there. And the background is this incorporation of OH, and that's the name relation to water peak. It's the easy name for that phenomena. Okay, any more questions? Okay, then the next one is G653, which is called the dispersion shifted single mode fiber. It was created in 1988, and it was meant to be used only for single channel networks. At that time, we didn't have yet wavelength division multiplexing. We have to recognize that this really was created in the late 80s at that time. It is also the first, what we call dispersion managed fiber, DMF. It was dispersion shift to 1550 nanometers. So the zero dispersion was moved from 1310 nanometer to 1550 nanometer. And I told you yesterday, we as fiber makers, we can do that by manipulating the core structure, by making a larger refractive index delta and do something on the core structure, some profiles in this core. We can manipulate it in this way that we increase the waveguide dispersion and move in this way the zero dispersion to higher value, 1550 nanometer. The idea behind that was that in this way we have an ideal combination of low attenuation. We have seen that. If you look to the spectral attenuation, this attenuation is the lowest at 1550 nanometer in that region. And we can combine it then also with the lowest dispersion. At that moment we thought that is the ideal combination. However, a few years later, when speeds went up and also when wavelength division multiplexing became important in increasing the capacity over one fiber, we have seen that this combination was not a very good combination, unfortunately. We found it later, unfortunately. So this fiber gives you quite some serious effect if you are using the fiber in dense WDM systems. At least also if you have equal channel spacing, which is normally the case. I will show you later what the effect will be. At this moment we have two categories, two subcategories, distinguished by the PMD value. And 653 is mainly in our books to have a maintenance for already installed links. It's not often used anymore, 653, for new networks. So 653 is more a result of the past, and at this moment is not much used anymore for new networks. I would certainly not recommend it in this way. Okay, then we have also shortly after the 653, we have also incorporated the G654 fiber, which is now named cutoff shifted fiber, but in the first editions it was also mentioned a loss minimized single mode fiber, and it's purely optimized for use at 1550 nanometer. Also the dispersion curve still has its zero dispersion wavelengths at 1310 nanometer. So you could also say it is a particular version of the 652 fiber. The dispersion curve is the same as a 652 fiber, but the fiber is more optimized for use only at 1550 nanometer. In some cases, some fibers in this category are, for instance, these pure silica core fibers I mentioned to you at the beginning of my talk yesterday. These fibers do not have any germanium content anymore, and these fibers show the lowest attenuation you can reach in silica at the moment. This fiber was specially developed and proposed by Asian countries like Japan, and they were promoting this fiber especially for their connections to the different islands they have, and optimizing the fiber to the lowest loss possible. So you see that this fiber is still used in several submarine applications. Because the use of the fiber is only at 1550 nanometer, these fibers are now characterized also by a higher cutoff value, and that's now reflecting also in the name of this fiber. Currently there are three categories, and mainly distinguished by differences in mode through diameter and or in the PMD value. Okay, any questions on this fiber, 654 fiber? And particularly a submarine type of application. Okay, before going then to G655, which is an important new class of fiber, I'd like to have a short intermezzo about nonlinear effects which can happen in fibers. Interactions with the medium that make the propagation sensitive to optical fiber. That is happening in nonlinear effects, and one of the effects is so-called the Kerr effect. It says the following, that the fiber refractive index is depending on the optical power which is passing through the fiber. So normally we have assumed so far that the refractive index of the glass is a constant. But if you really go to extremely high optical powers, which you can reach because of the invention of those optical fiber amplifiers, which boost the energy to high levels, we have seen that the refractive index can be influenced by the signal itself. And that can be reached in the following way. Either nonlinearities are creating, in case of a low effective area, that means if you have a very high concentration of your optical power in a small surface, so if you have let's say, a small mode for diameter, if all that energy you are passing through the fiber is in this very small area, then you can more earlier see this nonlinearity. So it's a concentration of optical power. And it is affecting also on long propagation distances. I show you here the formula which is often used to explain the Kerr effect. You see that the refractive index is the normal refractive index we know already, which is a function of the wavelength. And we are adding here a nonlinear coefficient to this, which is dependent on the power which is passing and also over the effective area. So you see if you have a large effective area, the influence of this parameter becomes lower, and with that the effect of nonlinearity. So this effect is particularly creating in optical amplified systems, and there it can create several effects, and especially if we are using also multi-channels, so multiple channels close to each other, we see the following. One effect is the so-called cross-phase modulation. In this case, the signal phase modulated proportionally to the neighboring channel power. So a neighboring channel can influence the phase of another channel, and that is resulting then in an increased noise level. There's also another nonlinear effect that is called the four-wave mixing, and this is the case when the generation of new spectral components are created which overlap with other channels. So let me explain this a little bit. You see here the effect of cross-phase modulation in two situations. On the left side you see the penalty, the noise level, which is created in a fiber with low dispersion. And on the right hand you see the same, but now in a fiber with a high dispersion. Now so far we have learned that dispersion is not a nice thing to have because it's broadening the pulses, so in general you like to reduce dispersion. However, here you see a positive contribution of higher dispersion because it is fighting this cross-phase modulation effect. You see here that in fibers with higher dispersion, this effect is almost zero. Well, if you have a fiber with low dispersion, you have serious problems, and certainly if you go to very tight spacing of your optical channels next to each other, then you can have a serious problem. So cross-phase modulation can be reduced, this effect, this nonlinear effect, by, first of all, by increasing. Okay, one interruption. The list for the lunches, is that already finished now? We are working on it. Okay. Sorry. Okay, so one way of reducing cross-phase modulation is to increase the channel spacings. That is one way to overcome that, but then you are, of course, limited. Then you cannot add so many channels anymore. On the other hand, you can also increase the local dispersion, and that's seen in this picture. So with increasing dispersion, you can also fight this cross-phase modulation effect. The other component I mentioned, the four-wave mixing, is shown over here. Again, two situations. Here a fiber with low dispersion, and on the right hand a fiber with high dispersion. And what you can see here, if you have a fiber with low dispersion and you have two channels, two optical channels indicated here with F1 and F2, you can get a mix of those products, and they are creating new channels over here at frequencies 2F minus F2 and 2F2 minus F1. So you can see that you are adding new channels, which can overlap, of course, with other channels you are aiming to place on this position. So that means there's a cross information of channel, and you don't want this situation. Again, this can be reduced. Four-way mixing can be reduced, again, by increasing the optical spacing. Then if you are increasing this distance, those components are falling further away and are outside the band. And also by increasing the dispersion coefficient of the fiber. Then you can also reduce those components, and you can see here those cross modulation products, you can see over here, are not present in this situation. So certainly we see also that dispersion also has a positive effect on your transmission. It has a positive effect on nonlinear effects. So reducing the impact of nonlinear effects in amplified dense WDM systems, that's in particular the situation. Amplified, so high intensities and dense WDM systems, many channels very close to each other. I just finished. We need to be sure that we don't have low dispersion in the wavelength band we are operating. And that means that we should not have a fiber like G653 for this example. The situation with this G653 fiber, where we really aim to very low dispersion, with a zero crossing even, that was not the best fiber for fighting this kind of effects. So that was the reason why, to replace 653 for this kind of applications, we needed a new type of fiber called non-zero dispersion shifted fiber. I hope this is clear why these new categories of fiber were created after the first start of G653 fibers. So this is the reason why the first next generation G655 fibers was created in 1996 for long distance, optically amplified, dense WDM systems, and replacing for those applications the G653 fiber. In this case, the zero dispersion is outside the C-band. At that moment, we were especially aiming for the C-band as the most common band for optical transmission in the third window. So that's the band from 1530 to 1565 nanometer. And currently, we have three categories in this class, distinguished now by low and medium dispersion, and the type of dispersion specifications. A box specification, I'll explain that in a moment, versus a pair of bounding curves specification. I'll explain you that in a moment. I saw, I believe, a hand from you. Do you have a question?
Thank you. I think I have confusion now when I think that dispersion sometimes has a positive effect on transmission. And in my mind, I was thinking that dispersion always have negative impact on the transmission. So my question is now, what is the dispersion? Really, dispersion is what? Because of those things you are saying, it has positive effect. Thank you.
Yes, good question. Because indeed, it is a bit a balancing act we have to play now. On one hand, we like to reduce dispersion as much as possible because it is causing pulse broadening. On the other hand, we have seen that for these very special systems, the high-dense WDM systems, you need a little bit more dispersion and not go to the zero values. So you need to have a kind of a balancing act between the optimization. Not too high, but also not too low. That is, in fact, the story behind this all. So if you, the highest dispersion, for instance, you have is 652 fibers. They have the highest dispersion. I will show you later some graphs. 653 fiber had the lowest dispersion. That was good for single channels, of course, because you don't have any interaction then with other neighboring channels. But if you go to multi-channels and high amplification, then 653 is not a good fiber. So you need then to increase the dispersion again. So it is a bit maybe confusion, but you have to see the balance between the ultimate regions, not as high as 652, but not as low as 653. So you have to be somewhere in between a 652 fiber and a 653 fiber. That is what a 655 fiber is doing. So this may be a surprise that dispersion also can have some positive effect on your transmission.
Thank you. I think, sorry, I'm going back to types of fiber optics types of fiber optics. We have seen many types of single mode fiber optics, I think, like cutoff and the other things. So I'm asking, based on what an operator have to choose a single mode fiber optics? Which criteria have to use to choose a fiber optics to operate?
Thank you. Yes, this is a very important question. I can understand that you have this question. But the story behind is that there are different optimization strategies. And you have to incorporate all the elements in an optical link to get your most wanted situation. Even 652 fibers can be used for long distances. It is possible, but in that case you need more dispersion compensating fibers, for instance, which is a negative part because it's adding more loss and more PMD to your system. But in principle, 652 fibers can also be used. 655 fibers are on a lower level of dispersion, so that is, it is needing less dispersion compensating, so that is positive, of course. 653 fibers, I would not recommend at this moment 653 fibers anymore. So the strategy you want to aim for is depending on what kind of strategy your system manufacturer is advising you to do. And some system manufacturers are just using 652 fibers with all the compensation effects, and other system manufacturers can advise 655 fibers. So it's not a black and white picture, so to say. There are multiple solutions possible, all with its own pros and cons to that.
Okay, back on his question. Sometimes one operator should say, I'm going to use 652D. Another one should say, I'm looking for 655. And the contractor, for example, should motivate one of them due to different reasons. Maybe the price, the cost, maybe the technology, I don't know. So now, as in this tutorial, it would be better to get really a clear recommendation on which type operators should look for. Thanks.
Add again, because as we are a regulator, I'm asking as a regulator. So sometimes you're putting some guidelines to that operators have to use. So sometimes you see he will use C, maybe D. Depends on what. I think it depends on. I can't say. It's based on what criteria he's using these types of fiber optics. That's why we're asking which types you can advise, especially here in Rwanda, these types of fiber different.
Yeah, again, I think there is not a fixed black and white picture around the choice of a certain fiber, because most of the fiber types, except maybe 653, I would not recommend that, can be used for long distances. The whole story is depending on the cost of a system. If you're using 652 fibers, again, you may have more cost because you need more dispersion compensating effects, but in principle, technically, it could be made. So it's an overall balancing act between the performance of a link and the cost associated to that. And the system manufacturer then is playing the role in which way he has optimized his system. So you have to speak with your system manufacturer and maybe with different manufacturers, offering the best solution for the given situation G655, we have already multiple components, multiple solutions available. Some companies are favoring a fiber which has a low dispersion slope. Other companies are offering fibers with a higher effective area. And a third optimization could be to have more dispersion compared to the other two. So this is an example in which we have already, within one group of 655, we have already 3, let's say, commercial available products in the market. The left one and right one are all inside G65D, and the higher dispersion fiber is in G65E. We call this 655D the low dispersion category, and the 655E is the medium dispersion category. Now, what can be reached with that? If you have a lower slope, you can have a very broad window available, even including the S-band. If that is your wish, you can have a decision on that fiber. And it can also make a quite easy slope compensation. If you go for a higher effective area, you have a higher slope also, so you don't have a very wide region. So S-band is not inside this fiber. The higher effective area is, of course, positive for reducing the non-linearity. For instance, you can place the different channels and a more narrow spacing to each other. And also you can use it for long distances. And the third optimization you can make inside 655 is allowing a little bit higher dispersion than the other two by using a medium dispersion fiber, which is again reducing harmful non-linearities. And it is the most narrow channel spacing can be used. Because you are allowing a little bit more dispersion, you can also space the channels at the most narrow way for this fiber. And the fiber can be used in the S-band. So again, it's up to you also to decide which of the 3 options you would go for, even inside 655. It's maybe a complicated story, but it is the reality. This is the way how fiber makers have put products in the market which are all somewhere placed inside 655. Is this complicated story? I realize that. Is that a little bit clear to you? Do you have any questions? Let me then show you how 655 has also been evaluated over the years. Up to 2003, we had A, B, and C class, and I show you here only the C class. The dispersion was specified in a very simple way, what we call a kind of box specification. We had only specification of the C band, so that is from 1530 to 1565 nanometer. Only a minimum and a maximum value were mentioned, both positive and negative. So that is called the so-called box specifications we had up to 2003. We as fiber makers thought that that was easy for that moment. But then around 2006, the system people from ITU came to us and asked us to have a little bit more clarification about the real dispersion curve over the wavelengths. And at that time we made an inquiry, and I was one of the leaders in doing that, asking the different fiber makers where their fiber products were available and showing which boundary levels we should incorporate. So we took care of all the commercial types available in the market, and we created this set of boundary lines. You will find that in the specification nowadays. And this is the region for what we call low dispersion fibers. So in this category, both the fiber type with a higher effective area can be placed, as well as the fiber with the reduced slope, which both can fit in this category of low dispersion. We also identified at that moment an E category, which is a category with medium dispersion, and you can see that those values are a little bit higher compared to the D version. And again, also here, we informed with the different fiber makers their products for this particular group of fibers. And so again, a group of boundary lines were defined, which you'll find back in the specification of G655. So it was moving from a simple box specification in 2003 to a bit more complicated, but more according to the reality of how the dispersion is changing over the wavelengths. And with that information, the system people could incorporate that in their system specifications. Any question on this development in times? So from 2003 to 2006? Oh, I had here the story already. Again, 2006, we needed a different specification than the box. And we created two categories, a low dispersion, the D fiber, and a medium dispersion, the E fiber. Okay, then in 2004, so that was still the time that we had the simple box specification for 655 fibers, a discussion started that we would also need a wider range over the wavelengths, and that created this new fiber specification G656, which is called wideband NZ DSF. The first edition was created in 2004, and again it was aimed for long-distance optically amplified dense WDM systems. In this case, the non-zero dispersion value is even outside, not only outside the C band, what we have in G655 fibers, but it's even outside the S band. So we have a very long wavelength range available for dense WDM systems. And currently we have only one category, only based on this pair of bounding curves, which I explained to you just a moment ago for 655. It only looks a little bit different. The fiber was created with this box specification, and also in 2006 we replaced it by this set of boundary lines, giving a little bit more real approach how dispersion is changing over the wavelengths. So we have in fact two NZ-DSF categories, 655 and this one 656. Any question on that? Okay, let's then go to the last one in this series. This is the recommendation G657, which is a bending loss insensitive single mode fiber, which was specially created in 2006 for the new market developing, that is the access network. So especially for access networks to houses and for networks inside houses, in which you in generally will have much more bending of your cable, of your drop cable, than for long distance type of cables. So it's supporting the growing worldwide demand in broadband services. And in 657 we have two main categories. The A category is for the access networks. It's going to the homes, but not in the homes itself. Offering improved bending loss and tighter dimensional specifications, both for improved connectivity. And this category is fully G652 compliant. And we also created a B category. These are aimed for the shorter distances, particularly for the in-building applications, which are generally a couple of 100 meters in general. So short distances only. and with further improved bending loss, so you can bend them more tightly than the other fiber types. This category also contains a low mode field diameter fiber, which was created in Japan, and the whole group, therefore, is not completely G652D compliant. Although there can be some components, some commercial solutions, which are 652 compliant. In total, we have here 4 subcategories. The recommendation was changed in 2009. So in the A category, which is fully 652D compliant, we have 2 subcategories, A1 and A2. And A1 is characterized to the minimum bending specification of 10 millimeter, and the A2 is characterized for a minimum bending radius of 7.5 millimeter. Now the B category, here you find improved bending sensitivity. B2 and B3 are the 2 subcategories in this class. B2 has the same specification as A2, but is not fully 652D compliant. And B3 is the best fiber we have in terms of bending in sensitivity, and it can be bent up to bending radius of 5 millimeter. So this is the situation we have inside G657. It can be visually indicated over here. If we have a bending radius, the minimum bending radius for a 652 fibers, you see it over here. For an A1 fiber, you can bend it up to 10 millimeter radius. A2 and B2, you can bend it to 7.5 millimeter radius, and the B3 fiber can be bent up to a radius of 5 millimeter. So these are the different bending specifications we have in this category. Here you see also the specifications for the different fibers, A1 and A2 at 1550 and 1625 nanometer. It goes too far to mention all the data, but you can find it in my presentation what the specifications are. And of course, these numbers are all available in recommendation G657. Now, to come back on the overview, what kind of fibers do we have altogether in the whole ITU booklet for fiber recommendations? You see here on top, the red one is the traditional 652 fiber, which has zero crossing at 1310 and a 1550 nanometer value of around 17 picosecond per nanometer kilometer. And for 657, that is almost the same small deviation, but almost the same fiber. It's also a non-shifted fiber. Then the first version of dispersion management was the 653 fiber, and you remember this was a minimum dispersion fiber at 1550 nanometer. But already quite soon it was taken over by 655 fibers, which are necessary really if you go to high optical amplification and to dense WDM systems. And this is the low dispersion fiber. This is the yellow one. An example of a large effective area fiber. You can also have in the same category of low dispersion a fiber with a lower slope. So you see here the green fiber is indeed showing a smaller slope than the yellow one. And for that reason it can be used over a larger wavelength range, as you can see. And finally the G655E fiber, which is the medium dispersion fiber, similar to G656, is showing a slightly higher dispersion, higher than the low dispersion versions from mentioned over here, but still clearly lower than G652 fibers. So you have here a set of different possibilities to optimize your systems, and in cooperation with the system people, you should make a choice which is the best fiber for your application and your solutions. And I propose that you also discuss this with the tutors giving the discussions on the different systems to come back on the question, which fiber should I use for which application? Okay? Any question? It is clear now what are all the difference, the details of the difference of all the different fibers. I highlighted a little bit more also to commercial fibers which are in the market. Of course, I cannot make a promotion here. ITU is an independent organization. They are not promoting commercial versions, but of course I can say that these are reflecting some commercial versions which are in the market without naming any one of them. Okay, here then an example. I made a comparison. I took two recommendations because we have not yet discussed them, but I promised them to you that I would show you two recommendations. Here, a recommendation of G652D, and on the right hand, the G655E. And let me have a look on some of the details. You see, for instance, as a fiber attribute, the whole list you see over here are fiber attributes. One of them is the mode field diameter. And if you compare 652 with 655, you see very clearly that the specification is different. For 652, the specification is only at 1310 nanometer, while for 655 fiber, it's only at 1550 nanometer. You could raise the question, but 652 fibers are also used at 1550 nanometer. Why not a mode field diameter specification for that wavelength as well? But already in my first explanation, I showed you that there's almost a fixed difference between the mode field at 1310 and at 1550. So we felt it is not necessary to add another specification here to that. There's always a fixed relationship between 1310 and 1550 nanometer mode field diameter. Now the way the mode field diameter is specified needs a little bit of explanation. You see, first of all, a range of nominal values is mentioned. In this case, you see a nominal range from 8.6 to 9.5 micron. So a fiber manufacturer can choose at a certain position in this range where he wants to optimize his fiber. And then on top of that, there is a tolerance of 0.6 micron. So this is the specification. We have to give a little bit of freedom for the different manufacturers to optimize their fibers. It also has a little bit of history. When I told you yesterday that in the very first days of optical transmission, the first fibers showed a very high mode field diameter of even 10 micron. And over the years, that has been reduced to smaller and smaller versions. A little bit of that is still visible in this large range which is there. My feeling is that in due course, also this range will be further limited, is my feeling. Because more and more people are interested in the lower mode field diameters, which give you better bending insensitivity. But this gives you a clarification why we have specified mode field diameter in this way. Similarly, also for 655, you see here a range of possible mode field diameters around which you should obey a certain tolerance. Okay, another parameter I'd like to discuss with you is the cutoff wavelength. You see here for 652 fibers, the cable cutoff is 1260 nanometer. So the systems can operate from a wavelength above this value, from 1260 and above. The fiber really is single mode. For the 655 fibers, this value is much higher because it's aimed to be used only at 1550 nanometer in this region. Then some questions, some remarks on the chromatic dispersion. If you see for 652 fibers, there is a quite simple specification, more or less. You see how it is specified. It's specified by means of a minimum and maximum zero dispersion wavelengths, running from 1300 nanometer to 1324 nanometer, and a maximum slope at the 0 point is specified. So this is the rather simple specification we are using for 652. On the right-hand side, you see quite complicated formulas. These are these lines which I showed you, the boundary lines which are agreed upon between the fiber manufacturers and the operators, that these are describing the dispersion performance of the fiber over the wavelengths from S, C up to L band. The next item I'd like to show you, and then I am reaching the cable attributes, which is the attenuation coefficient, for instance. You see for 652 fibers, we have a specification of the whole wavelengths from 1310 up to 1625 nanometers. So the whole wavelength band from O up to L band is in that range. with a maximum of 0.4 dB per kilometer. Additionally, it is said that the water peak, the 1383 nanometer, also should obey the same specification. That is the fact that we are talking here about the D version, the low water peak version. In 655 fibers, we do not have this large range. We only have a specification at 1550 nanometer and 1625 nanometer. So, of course, the use of the fiber is limited in attenuation specification. And finally, you see here the PMD specifications. In both cases, that is the same way. I explained to you yesterday on the section of PMD that we are describing this specification in terms of the number of cable elements we are looking for in a concatenated link, what the Q factor should be, 10 to the minus 4 probability that you will find a higher value than specified over here, and the value here for the D fiber is 0.20 picoseconds per square root kilometer. And that is exactly the same specification for G655. So that gives you, showing a little bit of highlights, the differences between 652 and 655 recommendations. Is there any question on that? I assume you have been using this kind of fiber recommendations in your work, I assume. Okay. Also,